Hi, all you cute cat and kittens out there. This is Miss Ducey with your physical science class, and for today, our objectives is that we're going to do some housekeeping. I have a question of the day for you, and mainly today we're learning about cations, anions, Lewis dot structures, and going over more things about oxidation numbers and bonding. So to start off, I have a little housekeeping for you. Thank you, first and foremost, so much to all of you for being really patient as we figure out technical difficulties with Schoology. I know it hasn't been easy, but thank you for communicating with me, and we're going to just continue to work through this together until our districts figure out a way that Schoology can handle all the influx of people at once. But so far, some tips that we've received from some amazing people at school is the following. When you enter Schoology, you have to go through the SS portal in my.bvsd.org, or else Schoology might not be working correctly. So please make sure you're using that single sign-on portal. If you find yourself there and you get that wonderful error page that we've all been seeing a lot, good tips and tricks is to try and just refresh, reload the page, or to log out of your account and try logging back in. You might find some times where Schoology might not just be working during our class periods. What I'd still want you to do is to be working on the assignments that I've given to you, and then just find a time later in the week to log back onto Schoology when it's working to actually submit them. And if your password isn't working, you should email Becky, our wonderful librarian. A little bit of an update on Google Hangouts. Last week I just made myself available during office hours as I'm kind of learning how this online school system is going to work. I've decided it's going to be more beneficial for our classroom if I'm available on Google Hangouts during our actual assigned class periods. So sometimes I'm going to mandate that you log on and that we're all in class online together. Sometimes it's going to be optional, but no matter what, I'm going to be available on Google Hangouts during our class time. The same Google Hangout link is going to work always. It's the link I've posted on the page a couple times. I'll post it again in the update for this week. Please save this link somewhere else. If Schoology isn't working, you can click on that and find me sitting there, and I could give you verbal instructions on what you're supposed to be doing instead of being frustrated and reloading Schoology all the time. And also, thank you for everyone for emailing me. I love hearing from you. Continue to email me. But just know I'm going to be available on Google Hangouts. So log on, say hi, even if it's just for like a 2-second quick question. I'd love to see you face to face. If you ever log on and for some reason I'm not there, just give it a second or send me an email. I might have just stepped away from my computer for a moment, but I promise I'll always be there. Okay, so this week, this is some assignments. So you should start to be getting used to this schedule, that under weekly schedule, you click updates, and I will post, as you kind of see here on the right of your screen, what looks like a very detailed instructions and agenda and a to-do list. So today and tomorrow, you need to complete your attendance quiz. You're watching this lecture video right now, and you're also going to need to check in with me via Google Hangouts at the end of this video lecture to kind of go over some of the things that we're talking about. So you must log into Google Hangouts today. Then Wednesday or Thursday, you're going to do attendance. You're going to watch a much shorter lecture video, and then most of your time spent in class is going to be completing a water molecule Mickey Mouse activity. Instructions are pretty detailed, but you're going to turn that in on Schoology by the end of the day on Friday. This is going to be another Google document submission. Lastly, to remind you, we have an ongoing semester chemistry lab project using PhET. You should have this PhET chemistry project. If not, it's in the materials on the main page on Schoology. Just to keep you on track, I'm not collecting this as we go, but it is one ultimate due date on May 15th. So to keep on track with the class, you should have done 3 PhETs last week. You should have done atom building, building a molecule, and isotopes and atomic mass. If you did not do those, make sure you're keeping yourself on track and you find times to complete those this week. Okay, so let's get started on today's lesson. So you have a take-home packet, and in one of those there's an assignment sheet starting the unit called bonding, which we are starting today. We're moving on from the atom. We still have a lot to talk about the atom. A lot of that information isn't going away. We're just adding on to it. So as you look in this packet, you should have this note taker. It's the very first page. That is what you need to take out today to take notes on. So we're going to start with our question of the day. I would like you to pause this video and take a moment to fill in these pieces of information in review of what we learned on the atom last week and last month. Okay, so now that you've taken a moment to do that, let's go through this. Your atomic number for fluorine is 9. The atomic mass is 18.99. We're going to round that mass number to 19. To find the number of neutrons, we take the mass number, and we're going to subtract the number of protons, because that's how many particles are in the nucleus. So when we do 19 minus 9, we get that there's 10 neutrons. We know that the number of protons and the number of electrons is always the same as the atomic number. And we're going to start to put those electrons onto our rings. So on the first level, it can only hold 2. We've used 2 out of our 9 electrons. On the second level, we're going to put the extra 7. Now, due to the rule of 8, we know that it could fit up to 8 electrons, but we already ran out, so there's no more on the third energy level. The total number of valence electrons, how many electrons are on that outermost level, is going to be 7. When you take a look at your periodic table of elements, we see fluorine over here in group 17, our halogens. So if we look at our oxidation number, which we've already labeled on our periodic table, we can see that for every element in group 16, the oxidation number is -1. But if we think about it, it also makes sense. Fluorine is in group 17, which means it has 7 valence electrons. It's going to be a lot easier for fluorine to steal 1 more electron to equal that happy rule of 8 than it would to give 7 away. If you like to steal electrons, you're negative, and fluorine only needs to steal 1 of them. So let's draw this fluorine atom. We're going to start with our element symbol of F and label that we have 9 protons and 10 neutrons. And with that, we have everything that should be inside of the nucleus. So we can start to create our rings of electrons. In our first ring, we can only hold 2 electrons. As we move to our second ring, we're going to have to fill in the other 7 valence electrons that we have. So we have 1, 2, 3, 4, 5, 6, and 7. So how many valence electrons does every element, except for hydrogen and helium, need in order to become stable? And by stable, I mean happy. And that is 8. This is known as the rule of 8 because all the valence electrons we need to completely fulfill an atom must be 8. So now we talked about ions before we left for spring break, but we're just going to review it. So an ion is defined as an element that does not have the same number of protons and electrons. And this can happen when we start to have bonding and some atoms are giving away their electrons to others versus some atoms are stealing electrons. It leaves an atom as an ion with an overall either positive or negative charge. For example, if we look at beryllium, how many valence electrons does beryllium have? Beryllium is in group 2 on our periodic table, so we can rightfully assume that it has 2 valence electrons. Will beryllium give away electrons or take on electrons to fill its energy levels? Well, if it only has 2 valence electrons, it's going to be a lot easier to give those 2 away than to get 6 more. So it's going to give those away, which gives it an oxidation number that feels really positive and happy to give them away of positive 2. Now there are 2 different types of ions. There's either a cation or an anion. A cation is a positively charged ion, which if it's positive, chemically speaking, that means it has more protons in the atom than it does electrons. Now for this, you can look at groups 1, 2, and 13 as all being cations. You can remember this, and you can also know that Miss Ducey loves cats, and cats make you feel really positive because they're the best. So cats are positive. They're the positively charged ions. Versus an anion is a negatively charged ion, which means that chemically it has more electrons than protons. We see this in groups 15, 16, and 17. So you should take out your colored periodic table. Pause if you have to look around for it. You already have the oxidation numbers filled out. So let's look at which one of these are cations and anions. Groups 1, 2, and 13 are all positive. They have more protons than electrons, so these are cations. Group 14, the carbon group, has an oxidation number of either positive or -4. Sometimes it's a cation, sometimes it's an anion. We're not going to go into the specifics of which it is when. And then you see groups 15, 16, and 17 are all anions because they are negative. They have more electrons than they do protons. This last group, our noble gases, is never going to have a charge. It's not going to be a cation or an anion because it equals the rule of 8 and it's always happy and it doesn't need to steal or give away any electrons. What do you do if you're a sodium atom? You have 11 electrons, one too many to have an entire shell filled. You need to find another element that will take that electron away from you. When you lose that electron, you will have full shells. Whenever an atom has full shells, we know that it's happy. So let's look at chlorine. Chlorine has 17 electrons and only needs 1 more to fill its 3rd shell and be happy. Chlorine will take your extra sodium electron and leave you with 10 electrons inside of 2 filled shells. You're now a happy atom too. You are also an ion, and you're missing 1 electron. That missing electron gives you a positive charge. You're still the element sodium, but you're now a sodium ion, Na+, and you have 1 less electron than your atomic number. So now you've become a sodium ion. You have 10 electrons. That's the same number of electrons as neon, but you aren't neon. Since you're missing an electron, you aren't really a complete sodium atom either. As an ion, you're now something completely new. Your whole goal as an atom was to become a happy atom with completely filled electron shells. Now you have those filled shells. You have a lower energy. You lost an electron and you are happy. So what makes you interesting to other atoms? Now that you have given up the electron, you are quite electrically attractive. Other electrically charged atoms, ions, and opposite charge, negative, are now looking at you and seeing a good partner to bond with. That's where chlorine comes in. It's not only chlorine. Almost any ion with a negative charge will be interested in bonding with you. So let's see if you're listening to my story. A little true or false for you. 1. True or false? Cations tend to bond with anions. And 2. True or false? An atom without a positive or negative charge can bond with another atom. Both of these are true. As you saw with the example of sodium and chlorine, one of which is a cation, one of which is an anion, they tend to bond with each other. but you don't have to necessarily have a positive or negative charge to form a bond. Bonds can form when electrons are either transferred or shared. Now we're going to look at a new way to represent this information. And we're going to start learning about a Lewis dot structure. So first, let's just see what a Lewis structure is. A Lewis structure, also called an electron dot structure, is a structural formula in which electrons are represented by dots. Two dots between atoms represent a bond. It was named from Gilbert Newton Lewis, who introduced it in 1916. The importance of a Lewis structure is that they're very important for predicting geometry, polarity, and reactivity of many compounds. So how do we draw Lewis structures? For individual atoms, the Lewis structure is drawn by first writing the element symbol. And then you place a dot around this element symbol for each valence electron available. There are 4 positions for dots to be placed. Most chemists draw them on the top, bottom, left, and right of the atom. Each of the 4 positions must receive 1 electron, or 1 dot, before any electrons can be paired with one another. This is due to the rule of 8. This rule of 8 states that in forming compounds and atoms, they must gain or lose or share electrons to give a stable electron configuration characterized by 8 valence electrons. At this point, you should be here on your note sheet. We're going to answer this question and walk through a few element examples. When drawing a Lewis dot structure, you must have 2 really important things: an element symbol, and you must know the number of valence electrons. So the first thing, and you're going to kind of follow through these examples with me, is to choose your atom and write down the element symbol. We're going to start with calcium, which is an element symbol of Ca. The next thing you need to do is count the number of valence electrons. I have a trick by looking at my periodic table. Since calcium is in group 2, I know it only has 2 valence electrons. I need to distribute those evenly across the 4 locations. You can either go to top, bottom, left, or right. I'm going to start by putting 1 electron on one side of calcium and the other valence electron on the other side. And that completes my Lewis dot structure for calcium. Let's try oxygen. I have my element symbol O. If I look on my periodic table to count my number of valence electrons, since it's in group 16, I know that there are 6 valence electrons. To distribute the electrons evenly, I'm going to go 1, 2, 3, and 4. I have to fill in all 4 slots around the element symbol first before I start doubling up and pairing the dots, in which I will go 5 and 6. So let's walk through 4 more examples. We have boron, fluorine, potassium, and carbon. I also, in this case, want to start looking at what the oxidation number for all of these atoms are, because it's going to help me when I want them to make their perfect match and pair. So boron has an oxidation number of +3, and it has 3 valence electrons, which would create a Lewis structure like this. Fluorine has an oxidation number of -1, and it has 7 valence electrons. And as we put them around fluorine, they should look like this. You have 6 paired electrons, 1 that is unpaired. Moving to potassium, our oxidation number there is +1. For potassium, it only has 1 valence electron, and so we can place it anywhere around the element symbol of K. Carbon could have an oxidation number of either +4 or -4, and it has 4 valence electrons, which we will evenly distribute around the element symbol. Now you should be looking at this table on your note sheet. We want to use the oxidation number and the Lewis dot structure to help us figure out how many of each element it's going to make to take. Now you should be at this point on your note sheet. We want to use the oxidation number and the Lewis dot structure to determine how many of each element it's going to take in order to create a bond. So let's start by looking at magnesium and chloride. How many of each element are we going to need? Well, we have magnesium, we have chloride. The oxidation number for magnesium is +2. And the oxidation number for chlorine is -1. Magnesium is willing to give away its 2 valence electrons, while chlorine has 7 valence electrons, and it desperately needs 1 more. This -1 oxidation charge means that it would need another chlorine in order to be neutral with magnesium. Magnesium has a +2 oxidation charge, chlorine -1. In order to get those two things and you bond together to equal 0, you're going to need 2 of those chlorine atoms. This means that if we were able to write an element out in its chemical bond name, we would have magnesium chloride 2. So as you're filling in this chart, you should draw magnesium with its oxidation number above it and its Lewis dot structure. You're drawing chlorine and writing what is the chemical formula for this bonding of elements. So let's try another one. We have lithium and oxygen. In order to create a Lewis dot structure for lithium, I have 1 valence electron with an oxidation number of +1. For oxygen, I have 6 valence electrons with an oxidation number of -2. I see I have -2 for an oxidation number on oxygen, but I only have +1 for lithium. So in order for those to balance each other out and equal 0, I'm going to need 2 lithium. As you can start to see, we write these chemical formulas with subscripts. I've written lithium subscript 2 oxygen using their element symbols. What this tells us as a chemist is that in order to make this chemical bond, in order for it to be neutral, you must have 2 lithium and 1 oxygen. So I challenge you to pause here in this video and attempt the next 2 element bonds. Alright, now that you're back, let's check your answers. You should have these 2 Lewis dot structures, and they're actually equal to each other, so there's no need to have multitudes of each element. You only need 1 for the chemical formula. For boron and oxygen, this one's a little bit trickier. We're actually going to need 2 boron and 3 oxygen in order to make the total charge of the bonds neutral. Now to finish our lecture today, my challenge for you is to look here on the side of your notes sheet and draw the following Lewis dot structures for each one of these elements. Once you have done that, it's important that you check in with me on Google Hangouts so that I can check for understanding and you can show me that you completed this worksheet and that you filled in these final Lewis dot structures. Thanks so much, everybody. I can't wait to see you in person.